Balance a binary search tree, problem 1382. So in this problem, you're given a binary tree as your input, and you have to return a balanced binary search tree with the same node values as your input. So a binary search tree is balanced if the depth of the two subtrees of every node never differs by more than one. So you can be guaranteed that your input is going to be valid, that it can be balanced. But in this binary search tree, you have your root node, and then to the left is going to be a value that's less, and then to the right is going to be a value that is more. Okay, so we're given this root. So in order to do this, what we can do is we're just going to traverse the tree and add all the values to a list. And then we can take that list, we can have it a list of integers, and then we can have another method, and we're going to say build a new tree with that list according to binary search tree. And then that's it. We can just return the new tree. So how are we going to traverse the tree? The simplest way is to really do DFS. So we can just say we're going to have our DFS, and we're going to pass the root into that. And then we are going to have the root after we build our tree. And then this is our main function, so traverse the tree. So we'll say DFS, and then we'll pass the root. Let's make this list globally available so that we don't even have to pass it anywhere. So we'll have a new array list of integers that we're going to add to as we do our DFS. And then we are going to return whatever we do in our build. So to just a DFS, very straightforward. We have our base case. So we can say if root is null, we are going to return. And then we're going to say DFS root left. And then we have we're going to add to our list if we are at our root. So we're just going to say root val, and then we're going to DFS to the right. So that's our simple depth first search, and what it will do is it'll add to the list all of the values as it traverses. So now when we build our tree, we are just going to take whatever was in our list, and we're going to find the center value and make that the root. So the center value will be, we're going to look at the left index and the right. And when we first call it, it's going to be 0, and then it's going to be the size of our list, -1. So those are the indexes of the list. And we will say, okay, if our right is less than our left, we are going to return null. But let's find our middle, and that is going to be our left index plus our right index divided by 2. Give some more space here in the middle. So our left, so that's going to be our mid. And let's make a new tree node. It's a new tree node. And we're starting to build our tree. And we're going to say L, get whatever is in the middle. And then what will our left will be, our node, our newly constructed node, the left will be, we're going to build it, but we're going to have our 0 is going to be the left, and then our right is going to be the mid -1, and then for our left, then for our right, excuse me, it's going to be build, and then it's going to be our mid 1 + 1, and then our right. And at the end, we are going to return our node. And then this should be it. So we're just creating our list, and then we're going through that list, and we are making our new tree. So let's run this. Let's do our, so when we start our tree node build, let's just print out our list and see what it is here. So you can see we just have our list here, 1, 2, 3, 4, 1, 2, 3, 4. And so that is, we're just finding the index. And so we have our list that's constructed in our DFS. And then from there, we are going to say whatever our mid is. We can say and then we can just write mid. So we'll see here our mid is index 1, the mid is index 0, our mid is index 2, and our mid is index 3. So if the right is less than the left, we are returning a null here, and that's how our tree is constructed. And I think that should be it. Okay, thank you. If this helped you out, please subscribe.